In this video, we are going to study regarding the design of RCC slab. So let us see now. If you see this figure, in this you can see there are some portion. You can see now this is one slab. This is another slab. You can see these are the column portion. The next these are the beams what we have. So now let us see what is the slab and why it is being used and how we have to design that slab. So let us start now. Slab is nothing but a two-dimensional or a planar element used in all types of structures such as floors and roof coverings. So slabs are nothing but the plate elements which are having depth d much smaller than its span and width. So usually what happens is that they are carrying the uniformly distributed load and from the floors or the roof of the buildings. The thickness of the slab is very small as compared to its length and width. If you compare the thickness, it is very less compared to the length and the width. Then next is if you see the classifications of the slab, so slab can be classified based on many aspects. One is slab can be classified based on shape, that is we can have a square, rectangular, circular or polygonal, etc. Then next is if you see based on the type of supports, that is slab supported on walls, slab supported on beams, slab supported on columns, etc. Then next is based on the support or boundary conditions. If you see, we can classify it as simply supported, cantilever, overhanging, fixed or continuous slabs. Or based on the use, if you want to classify, we can classify it as roof slab, floor slab, foundation slab, etc. Then next is based on the cross sectional configuration. If you want to classify, we can have it as a grid slab or ribbed slab, what we say, solid slab, filler slab, etc. Then next is based on the spanning direction. The slabs are classified as based on what you can say Ly by Lx ratio. Ly and Lx ratio are nothing but the length of the span. L is nothing but the length of the span, that is length of the longer span to the length of the shorter span. So Ly always it is length of the longer span to the length of the shorter span. Based on the spanning condition, the slab classified as one-way slab and two-way slab. Based on classification of what is based on the length of the longer slab, longer span, it is being classified as one-way slab and two-way slab. So now let us see what do you mean by one-way slab. So here if you see there is one slab, we have one dimension, that is Lx we have, and another dimension Ly we have. So here you can see now we have length Lx and Ly. So if you see, if the ratio, that is Ly by Lx, if it is greater than 2, if it is greater than 2, then we can call it as a one-way slab. We can call it as a one-way slab. Then next is if you see, if the Ly by Lx ratio, that is Ly by Lx ratio, if you compare, if it is less than or equal to 2, if Ly by Lx ratio, if it is less than or equal to 2, then we can call it as a two-way slab. Two-way slab. So now what usually students they get confused, what is this, what we have to take Ly and what we have to take it as Lx. So in other words, what you can remember is that length of the longer span to the length of the shorter span. Length of the longer span to the length of the shorter span. Always longer divided by shorter span. If it is greater than 2, then we can call it as a one-way slab. If it is less than or equal to 2, then we can call it as a two-way slab. So now further let us study regarding this, how it is going to behave. So if you see like this we have one what you can say columns we have on all the four sides and which is being supported by beams. So if you see the behavior of this slab, you can see that if you see the to a one-way slab, you can see we have Lx we have and Ly we have. If Ly by Lx, if it is greater than 2, we can call it as a one-way slab. We can call it as a one-way slab. If the slab is supported on only two sides, then we can call it as a one-way slab. If you see in this, what's happening is that, so load, what you can say, which is transferred, it is only transferred in one direction. You can see only it is transferred in one direction. So therefore we call it as a one-way slab. If you compare it with a two-way slab, so here in this case what happens is that load is transferred in both the direction. You can see in this direction the load is transferred, and in this direction also what happens that the load is transferred. In both the direction what happens that load gets transferred. So therefore we call this as a two-way slab. Therefore we call it as a two-way slab. So if you see the bending, how it is going to bend, so if you see this is the one-way slab, so what happens that only in this direction, whenever if the ly by lx ratio, if it is greater than 2, what happens that our slab is going to bend only in one direction, only in one direction, right? So therefore what happens is we are going to, along the shorter span it is going to bend. So therefore what reinforcement we are going to provide, that is main reinforcement, it is along the shorter span. So if you compare it with two-way slab, so in this direction also it is getting bent up, and in this direction also it is getting bent up. You can see here now, in this way also it is bending, and in this way also it is bending. In both the directions it is bending. So the reinforcement what we are going to provide, so it will be main reinforcement in both the directions. Whereas if you compare it with one-way slab, you can see here in this figure only in one direction they have provided the bent up bar. In another direction they have provided the straight bars. So one thing what we can remember is, in one-way slab we are going to place the main reinforcement along the shorter span. Why? Because bending happens in that direction. When it comes to two-way slab, in both the directions our slab is going to bend. Our slab is going to bend. So therefore in both the directions we are going to provide the reinforcement. Then next let us see now design of one-way slab. So this reinforced concrete slabs supported on two sides with their longer dimensions exceeding two times the shorter dimensions. This, the Ly is nothing but longer dimension. If you cross multiply here, that is two times of the shorter dimensions. That means if the longer dimensions, if it is exceeding two times the shorter dimensions, then we can call it as a one-way slabs. Or this type of slab is also called as slab spanning in one direction. Slab spanning in one direction, as the bending takes place only along the shorter span. Bending takes place only along the shorter span. So therefore what we do, we are going to place the main reinforcement along the shorter span. The one-way slab is analyzed by assuming it to be a beam of 1 meter width. So the analysis what we have studied till now of a beams, similar to that itself we are going to design a slab, but we are going to assume the slab as a beam of 1 meter width, and we are going to analyze the problem. Then next is, for a given type of support condition, the span to depth ratio applicable for the beam in IS 456 is also valid for slabs. So what are support conditions we have studied for beams, same thing it is being applied for the slabs also. Then next is, normally the slab thickness of the slab is so chosen that shear can be resisted by the concrete alone without any extra shear reinforcement. So usually what we do, we are going to provide the thickness of the slab in such a way that we need not provide any shear reinforcement. We need not provide any shear reinforcement. That shear is resisted by the concrete itself. Why? Because what happens that the width of the section will be larger, so therefore shear is resisted by the concrete itself. So therefore we don't require any extra shear reinforcement. The next is two-way slabs. The slab which is supported on all the four edges and having Ly by Lx ratio as less than 2, then we can call it as a two-way slab. The slab which is supported on all four edges as well as which is having the Ly by Lx ratio as less than 2, then we can call it as a two-way slab. This two-way slab is also called as slab spanning in two directions because bending takes place in both the directions. Therefore what happens is that as the bending takes place in this direction also as well as in this direction, x direction as well as y direction, so therefore what happens is the main reinforcement is provided along both the directions, that is in two way. If you compare, or let us see the difference between the one-way slab and two-way slab. So if you see one-way slab, Ly by Lx ratio it is greater than 2. If you compare it with two-way slab, Ly by Lx ratio is less than or equal to 2. Then next is the bending takes place only in one direction, that is in the shorter span. But when it comes to two-way slab, the bending takes place in both the directions. Bending takes place in both the directions. Then next is depth required is more. Depth required is more as in case of one-way slab. So in two-way slab, depth required will be lesser. Then next, as the bending takes place only in one direction, that is along the shorter span, so therefore main steel reinforcement is provided along the shorter span. So whereas in the case of two-way slab, main steel reinforcement is provided along both the spans. This one-way slab is less economical as thickness is more and the amount of steel is also more. Whereas when you go for two-way slabs, it is more economical as the thickness of slab will be less and the amount of steel required will also be less. So these are some of the basic differences between the one-way slab and two-way slab. Then next we will try to see some of the criteria which are being used in the design of the slabs. So first we'll see regarding the deflection control. So for slabs, the vertical deflections limits are specified by maximum L by D ratio, that is length to the effective depth ratio. So therefore basic values of span to effective depth ratios for span up to 10 meters, it is given by, for cantilever it is 7, for simply supported it is 20, and for continuous it is 26. Already this we have studied in the beams also. Then afterwards, if the span is greater than this 10 meters, that is for spans about 10 meters, this value may be multiplied by 10 per span in meters, 10 per span in meters, except for the cantilevers in which deflection calculation should be made. Then next is for slabs spanning in two direction, the shorter of the two spans shall be used for calculating span to effective depth ratio. So when we are designing what you can say two-way slab, the shorter of the two spans shall be used for calculating the effective depth ratio. For two-way slabs of small spans up to 3.5 meters with mild steel reinforcement, the shorter span to overall depth ratio may be used to satisfy the deflection limits for loading class up to 3000 Newton meters. So what we have to do is that we have to use the shorter span to depth ratio, to satisfy the deflection limits. So for simply supported it is 35 and for continuous slab it is 40. For HYST bars, the values given above should be multiplied by 0.8. This is for mild steel, and if you are calculating for HYST bars, it has to be multiplied by 0.8. Then next is what should be the minimum reinforcement provided in the slab. The area of reinforcement in either direction in a slab should not exceed 0.15% of total cross-sectional area in case of mild steel. So 0.15 for mild percentage of total cross-sectional area for mild steel, and for HYST it is 0.12, and in case of HYST bars this value will be reduced to 0.12%. Then next is what is the maximum diameter of the bar that can be used. The maximum diameter of the reinforcing bar in a slab should not exceed 1/8 of the total thickness of the slab. Then next comes is regarding the distribution reinforcement. So now why distribution reinforcement is provided, let us see. So this distribution reinforcement is provided in the longer span of one-way slab. In the shorter direction we provide main reinforcement. In the longer direction we are going to provide the distribution steel. The steel is as per the minimum reinforcement criteria given above. The next is what is the function of providing this distribution steel. So to distribute the concentrated loads coming on the slab and to protect against the shrinkage and temperature stresses, to keep the main steel bar in position, and the distribution steel is kept above the main steel. So what it means now, so main steel has to be placed at bottom and distribution steel has to be placed at top. Then next is what should be the spacing between those reinforcement. So one is minimum distance between the bars. The minimum horizontal distance between the two parallel main bars shall not be less than, first one is the diameter of the bar. That is, the largest diameter of the bar has to be considered. The minimum horizontal spacing. So that is shall not be less than, first one is diameter of the bar, that is largest diameter of the bar, 5 mm more than the nominal maximum size of the course aggregate. 5 mm more than the nominal maximum size of the aggregate. Then next is the vertical distance between the two layers of the main reinforcement. So for example, if you have one bars, three bars, if you have another layer of bar, if you want to put, the minimum vertical distance between two shall be more than 50 mm, or two-third the nominal maximum size of the aggregate and maximum size of the bar. Then next is what should be the spacing of the reinforcement, that is maximum distance between the bars in tension. The spacing of main steel in the slab should not exceed the following. The spacing of main steel in a slab should not exceed the following. First one is that 3 times the effective depth of the slab, that is 3D or 300 mm. 300 mm. This it should not exceed what you can say 300 mm. Then next is the spacing of the bars provided to act as a distribution steel are provided for preventing temperature and shrinkage stresses shall not exceed the following, that is 5 times of D or 450 mm, that is 5 times of the effective depth of the slab or 450 mm. So in the previous case it was 300 mm for main reinforcement and 450 mm for the uh, distribution steel, and it is 3 times the effective depth here for main reinforcement and 5 times of D it is for the distribution steel. Then next is what should be the cover which has to be provided. Nominal cover to be provided in a slab is 20 mm, and the other values of cover for different environmental conditions are listed in table 16 of IS 456. If you refer IS 456 in table number 16, they have given the cover. Then next is regarding the reinforcement in the bar itself, that is regarding the bent up bars. Some of the main reinforcement in a slab are generally bent up near the support to take up the negative moment which may be developed due to the partial fixity. So what happens that, for example, if this is the main reinforcement which we have placed, so we are going to bent up these bars near the supports. So as to resist the negative moment. Generally what we do is we are going to provide the alternate bars, that is bent up bars. For example, if you take one slab, so what happens that one bar we are going to bent up here, next bar will be straight, second bar will be bent up, third will be straight. In that way what happens that we are going to do alternate bent up of the bars. So generally alternate bars are bent up at a distance of 0.15 L or L by U, L by 7, 0.15 L or L by 7 from the center of the support. From the center of the support. The bars available at the upper face should be more than 1/10, that is 0.1 L from the center of the support. So you can see 0.1 L from the center of the support. So one bar we have to take straight, one bar we have to go take it to the top, so as to resist the negative movement. So 50 percentage bars are bent up bars. Then next is regarding the shear design. So already I had said, once again I repeat, slabs are safe in shear. Why? Because since the nominal shear stresses is very low, because width is large, therefore no reinforcement is provided in the slab except that the alternate bars are bent up near the supports. So usually what we do, we are going to do the bent up near the supports. So here in the slab design we don't provide the shear reinforcement. Why? Because nominal shear stresses is very low, because width is very large. Then next is what all loads they are going to come on the slab. So there are various loadings which are going to come on the slab. One is self weight. So self weight of the slab we are going to have. Then next is live loads. That is what is given in IS, it is 875. Then next is finishing and partitioned loads. So as to get all these loads, what we can do, we can refer the code that is IS 875. So from this we can take the loads and we can put it on the building and we can design the structure.